Hi everyone. So today we're going to continue on 11.3. So last video we talked about theorem 11.3.1, which told us that if you have a linear, non-homogeneous linear function equation, a linear operator equation, the solution is always a combination between a particular solution and a homogeneous solution. So therefore now it's just a matter of trying to find those two things and put them together to form the solution to a linear operator equation. So if you think about it, let's say we're given a linear constant coefficient differential equation in the form of L of y equal to some function f. So here L would be basically would be a differential operator that have constant coefficient, and if you want to know what L will look like, well actually we saw that right here. Okay, right here. D squared plus 2d plus 1, that would be what we consider to be the L, the linear operator that involves differential operator inside. And this equation is definitely non-homogeneous unless f is 0, which we're going to say that f is not 0. So given this linear constant coefficient differential equation, we know that the homogeneous solution can be formed by the following. Y sub h can be found using what we call characteristic roots method, which is what we learned in 11.1 and 11.2. So the question comes down to how to find y sub p. And we will talk about two different methods on how to find y sub p. One of them is called undetermined coefficient method. The other one is called variation of parameter method. So that will be what the next two videos is going to be about. But before we get to those two methods, we actually might start one of them this video. But before we get to those two methods, I do want to point out something that's interesting that we also want to use too. To find y sub p, we can often take advantage of the fact that we have a linear operator. And what do I mean by that? Well, let me show you. I'll take advantage of the fact that L is linear. So imagine the following. Let's say if we want to find a particular solution, oops, to a differential equation, L of y equal to a1 f1 plus a2 f2. So in here, this whole thing collectively become our function f. But we just simply kind of break down function f into smaller, simpler function. Like in this case, function f could be e to the x plus cosine x. Then we'll probably call f1 e to the x and f2 cosine x, so that we can kind of further separate it. The question would probably be, how would that help us? So let's say if we want to find a particular solution, this function L of y equal to a1 f1 plus a2 f2, we can simply do the following. We can simply find two functions, which I'm going to call them y1 and y2, such that this is true, such that L of y1 give you f1 and L of y2 give you f2. Now the question then is, how does it help? Well, because L is linear, the function y equal to a1 y1 plus a2 y2 will now satisfy this equation. oops, 2 How? Well, let's take a look. Let's say I'm going to put L of y. So what is y? Well, y is a1y1 plus a2y2. Based on the fact that L is linear, I can separate and pull out the constant. So therefore become a1 L of y1 plus a2 L of y2. And since we already know L of y1 is f1 and L of y2 is f2, then this just equal to a1 f1 plus a2 f2. Notice the important part here is that we don't need to know that y equal to a1 y1 plus a2 y2 is the only solution to the differential equation. I just need a solution, and it will be a solution because I just checked it and showed that it works. Okay, so one of the things that you often get confused is that sometimes when we're looking for a particular solution, there's no unique particular solution. Okay, we just simply try to find one of them. And here the idea now is that if I do have a very complicated function f, I can actually break down function f into smaller function f1, function f2, function f3, function f4, and so on and so forth, and then try to now find solution for each one of those, which are now less complicated. And then once I find those, I can put together to form the solution. The way to do this method right here has a name. When we use this method to find solution to a differential equation, this method is called, or is referred as the superposition principle. And what does it mean by superposition principle? Well, we'll state formally, but just the idea is that because the desired solution, which is y, is found by superposition, and yes, superposition is a very fancy math word, but what does the word superposition basically mean? It means addition. Yes, I know. Then why doesn't it just call addition principle? Well, because superposition principle sounds a lot more impressive than addition principle. That's why. So it's superposition of solution of more than one equation. So the idea of superposition principle is that instead of solving one very complicated function f non-homogeneous differential equation, we break it down into simpler non-homogeneous differential equation using f1, f2, f3, f4, and on. And then once I find all the solution to those, we combine them together. Now you might be thinking, like, isn't that more work? Well, let me show you some example, and then you see how that works out. But before we do that, how about we state the superposition principle, formally. So here what superposition principle is for us in differential equation in this class. Let's say given a linear operator L of y, and let's say we have an equation L of y is equal to a1 f1 plus a2 f2 plus dot 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 plus am fm. Okay, then the solution to this equation will be in the form of y equal to y sub h, that's the homogeneous solution, plus a1 y sub 1 plus a2 y sub 2 plus dot 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 plus am y sub m. So collectively, these right here become our y sub p, our particular solution. But our particular solution is actually formed by a whole bunch of smaller solution. In this solution right here, where we know the following is that L of y sub h would give me 0 because that's the homogeneous solution. L of y sub 1 would actually give me the solution f1, and L of y sub 2 would give you f2, and this go on until y of f sub m, which would give you fm. So therefore, this superposition principle basically allows us to further break down our solution to just homogeneous as well as a particular that can be formed by multiple function itself. And with the superposition principle along with our homogeneous solution, we can now actually kind of fairly accurate predict how many terms our function, our equation, the solution should have. Okay? And we'll talk about that when we get to an example. So how about we look at a very simple example. Imagine the following. Imagine I ask you to solve for this. Suppose I ask you to solve this equation. Y double prime plus 2y prime plus y is equal to e to 3x plus 1. Okay? So in here, let's try to break this down first. Let's try to break it down. So I'm going to rewrite this into a differential operator form. So that would be d squared plus 2d plus 1 of y equal to e to 3x plus 1. Now let's try to break this down. So this is our L. So this collectively is our function f. But our function f in this case is actually formed by two functions, f1 and f2. Which one is f1? F1 would be e to 3x, and f2 is 1. So therefore, in this case, I can say that f is e to 3x plus 1, where I can say f1 is e to 3x, and f2 is 1. And so f will be f1 plus f2. And our linear operator L is d squared plus 2d plus 1. Now let's try to understand what the solution would look like. So what would the solution look like? So remember, our solution would be y equal to y sub h plus y sub p. And in this case, our y sub h should be dimension 2. Meaning they should have two terms with two arbitrary constants, C1 and C2. How do I know that? Because this is a second order differential equation. Now look at our function f. Our function f is actually formed by two separate functions, e to 3x and 1. So therefore indicate that we will also have two separate functions, y1 and y2. y1 to be the solution of e to 3x, and y2 be a solution of 1. And then y sub h will be a solution to L. So therefore, in this picture, the L would determine what y sub h will look like. F1 would determine what y sub 1 look like. And F2 would determine what y sub 2 look like. And that's how we go put together our function. Our solution. Our solution will still be two-dimensional. It would no longer be a subspace because of the y1 and y2 would translate our homogeneous solution to a different spot. Now, let's try to put this solution together. Now, if you look, this equation, we actually know something about it already. If you look, go back to your note from yesterday. Notice that we actually solved the equation y double prime plus 2y prime plus y equal to e to 3x already. Meaning, we already know some part of this solution, and we don't have to go through the whole thing. In this case, we already know the following. We already know that y sub h is actually c1 x e to the negative x plus c2 e to the negative x. That doesn't change because that is unique to the differential operator d squared plus 2t plus 1. And if you're doing any differential equation with d squared plus 2t plus 1 as the linear operator, you always have the same exact homogeneous solution right here. Now for f1, so this is basically dictated by L, which is equal to d squared plus 2d plus 1. And now our f1 equal to e to 3x would dictate our solution of y1, which is equal to 1 over 16 e to the 3x. So now comes the big question. What happened to f2? f2 equal to 1. What is y2? So that's the only thing that we need to figure out. And once I figured this out, I would have everything I need to put together the solution. Now, it's actually not too hard to figure out what is y2. So what does y2 have to do? Well, y2 have to satisfy this equation. And that's actually a very simple solution to this differential equation. And if you take a minute to think about it, you might be able to find the solution simply by observation. And I'm going to suggest that you pause the video and give yourself like 2-3 minutes just to look at it and see if you can figure out what would be a possible solution for y that would satisfy this equation. Okay? So hopefully you took a few minutes to look at it and come up with a solution. If not, the very simple solution is this. It's just y equal to 1. And the reason why y equal to 1 would work, because if y equal to 1, y double prime and y prime are both 0. So therefore, the right side of the equation becomes 0 plus 0 plus 1, which obviously equal to 1. So therefore, I can now say that y sub 2 is actually 1. So now we found this. And now I'm going to apply superposition principle and say that our solution y would equal to y sub h plus y sub 1 plus y sub 2. And therefore our solution would be c1 x e to the negative x plus c2 e to the negative x. So that's the homogeneous solution. Plus 1 over 16 e to 3x. That is a solution unique to f1 plus 1, which this solution is unique to f2. I would suggest that you try to find the first and the second derivative of this function right here, and then try to see if you can plug it into our differential operation d squared plus 2d plus 1, and see if that actually come out to be e to 3x plus 1. Now, how about we do another example? How about we add on to this? What if now I ask you to find this? So now, how does this one work? So, well, the same way, because, and if you think about it, you can count how many things you need to complete this solution. So first of all, we need 2 things for the homogeneous solution because second order. And then because we have 3 separate functions in the non-homogeneous part, that would mean that I also need 3 things in a solution set. So therefore, we should have 5 things total. And as a matter of fact, in this case, we already know what we need for e to 3x as well as 1. So the only thing we have to figure out is e to the negative x. So in here, once again, we're going to do the exact same thing. I'm going to go and say, write it into differential operator form. D squared plus 2d plus 1 of y equal to e to 3x plus e to negative x plus 1. Okay. And I'm going to identify that this is my L. This is my F1. This is my F2. This is my F3. So our solution y should look like y sub h plus y sub 1 plus y sub 2 plus y sub 3, where the L dictate what f of y sub h will look like. f1 dictate y sub 1, f2 dictate y sub 2, f3 dictate y sub 3. In this case, we already know some of these already, so let's try to figure it out. We already know that y sub h is going to be equal to c1x e to negative x plus c2 c2 e to negative x. We also know what happened to y1, e to 3x. The corresponding solution y1 would be 1 over 16 e to the 3x. We don't know what y2 is. That's what we need to figure it out. But we do know what y3 is. y3 is just 1. So we just have to figure out what y2 is. So how do I figure out y2? So y2 basically looking for the particular solution that works with e to negative x. So to find y2, oops, we need to solve the equation y double prime plus 2y prime plus y equal to e to negative x. So the process to do this is exactly the same as what we did before. We can simply just do the following. So that is d squared plus 2d plus 1 of y equal to e to negative x. That means it's d plus 1 of d plus 1 of y equal to e to negative x. We're going to do the exact same thing just like what we did before. As a matter of fact, I would suggest that you should pause the video and try to go through the process on your own. Just mirror what we did in the first example from yesterday's video. But I'm obviously going to continue. I'm going to let d plus 1 of y equal to u, and therefore d plus 1 of d plus 1 of y equal to e to negative x turn into d plus 1 of u equal to e to negative x, and that means u prime plus u equal to e to negative x. Notice that the process is exactly the same. Our exponential multiplier is m is equal to e to integral 1 dx. So therefore it's e to the x. So I'm going to say e to xu prime plus e to xu equal to 1. Because e to x times e to negative x is 1. Therefore, that tells me that e to xu prime is equal to 1. So e to xu would simply equal to x plus some constant c1. And therefore, multiply the entire equation by e to the negative x would give me u equal to x e to negative x plus c1 e to negative x. And now I'm ready to do my second integration. So therefore now that means d1 of y would equal to u, which is x e to negative x plus c1 e to negative x. So once again that becomes y prime plus y equal to x e to negative x plus c1 e to negative x. So the exponential multiplier is exactly the same as e to the x. So therefore meaning e to xy prime plus e to xy equal to x plus c1. And so this just becomes e to xy prime equal to x plus c1. And so if I integrate, it becomes e to xy equal to 1/2 x squared plus c1 x plus c2. And now multiply everything by e to negative x, give me y equal to 1/2 x squared e to negative x plus c1 x e to negative x plus c2 e to negative x. Notice that this is just our y sub p, which we already know. And so this part is our y sub 2. Because this part would be the particular solution that's unique to e to negative x. So now I think I'm ready to form my solution. So now I know that our solution y for the equation, so therefore maybe I should write this. So for the equation y double prime plus 2y prime plus y equal to e to 3x plus e to negative x plus 1, we know that y would equal to y sub h plus y sub 1, y sub 2, y sub 3, where y sub 1 goes with e to 3x, y sub 2 go with e to negative x, and y sub 3 go with 1. So now what is this solution? Well, we'll look something like this. We'll have c1 x e to negative x plus c2 e to negative x plus, for y1, which is correspond to e to 3x, is 1 over 16 e to 3x. The solution corresponding to e to negative x in this case is 1/2 x squared e to negative x. And then the solution corresponding to 1 is just 1. So therefore, this becomes the solution to this differential equation. So notice that the important idea here is how to count how many terms you should have in your general solution to a non-homogeneous differential equation. And remember, that's based on how many terms you have in your homogeneous solution and how many terms do you have in your particular solution. And it's very easy to identify them. The homogeneous solution would have the same number of terms as the order of your differential equation. And your particular solution should have the same number of terms based on how many different functions form the function f. So the more you use to form function f, the more terms you have in your particular solution. The higher order of your differential equation or differential operator, the more terms you have in your homogeneous solution. All right. Unfortunately, I think this is all the time I got for today. So tomorrow's video, we'll focus on talk about one of the two methods that you need to know for finding a particular solution. All right, I'll talk to you guys tomorrow. Bye-bye.